Hello everyone, Mr. Minnick's my name, math is my game, and today in this lesson what we're going to be looking at is pertaining to polynomials. We're in the second section here of chapter 5. The first section we talked about how to name polynomials based on their degree and the number of terms that they have. And in this second section we're going to kind of ease our way into polynomials. The second section should be real easy. If you successfully, that's kind of a big contingency there, if you successfully understood how to solve quadratic equations by the technique of factoring, then this should be a really simple section for you to understand. The Common Core Content Standards, FIF 7C, graph polynomial functions and identify zeros when suitable factorizations are available in showing end behavior. So we had mentioned the end behavior business before, so let's just kind of go back for a minute to chapter 4 if we could. Chapter 4 we saw something like this: y equals x squared minus 5x plus 6, something like that. And that's a standard form quadratic function. Standard form doesn't really help us much because all it really tells us is that the y-intercept is 6. We know that the quadratic function in question, because of the a value of 1, would open up from the vertex, wherever the vertex is, we'd go over 1 and up 1. And so this function, would have that kind of shape to it. But beyond that, we really can't do much unless maybe we put this thing into a different form. So in chapter 4, section 4, we talked about factoring. So if we just look at this quadratic expression, just that expression, we know how to factor that. X squared minus 5x plus 6 would break down into two binomials, x minus 2 and x minus 3, of course. In the context of solving an equation, we would have that equal to 0, and so we'd get our solution set of 2 and 3. In the context of a function, what we would have is x-intercepts at x equals 2 and x equals 3. Okay, so we'd have a function that kind of does something like that. So the big idea here, the big thing to take home is the fact that these x-intercepts are the same thing as the solutions to the equation, are the same thing, and they're kind of counterintuitive to the factors. X minus 3, positive 3. X minus 2, positive 2. If all that makes sense to you, then this section is going to be real easy. There's really only one more thing to consider, and that's what happens whenever there's a factor that occurs more than one time, or a factor that's exponentiated, if you would, to some power. Okay, that's really about the only thing beyond what we've seen so far that you're going to run into. So you're also going to need to recall all those things about end behavior. Remember, there were 4 scenarios with end behavior. With the end behavior, we could have some graphs that go and do the same thing on both ends, or we could have graphs that do opposite things on both ends. We could have something like this, something like this, something like this, or something like this, right? So in the case where we have the graph doing the same thing on both ends, remember the degree of those functions would be even. The degree would be even. So the degree in the other case then would be odd when the functions do the opposite things on both ends. And the function does opposite things on both ends. And then remember we said if we look at the right side, if the right side's going up, then the leading coefficient is positive. The leading coefficient's positive. So that's going to happen here and here, right? The leading coefficient's positive. And then over here on the right, we're going downward. The function's end behavior is downward, so the leading coefficient would be negative there. Okay. So you're going to need to know those ideas, and if you do, this section's going to be a cakewalk. Notationally, it's going to be scary, so I'll kind of forewarn you that the notation is kind of scary. So by the end of this lesson, you should be able to analyze a polynomial that's factored. You should be able to write a polynomial function from its zeros. So they're going to tell you, hey, this polynomial function has these x-intercepts. You should be able to write that polynomial in factored form, and then maybe even in standard form, because you can expand that out. Okay? So there might be a little surprise there as far as foiling and then multiplying a binomial by a trinomial or something like that. So anyway, this first paragraph, they're kind of basically saying what I just said. The notation, like I said, they're using subscripts, r's and n's and x to the n minus 1 and all that. Don't worry about the notation. You get the general idea of this. So let's just go right to our first example. Our first example, they're asking us to factor something. So we're going to need to know how to factor. Well, if I take this expression, x cubed minus 2x squared minus 15x, one thing you should notice is that each one of those three terms has a common factor that can be factored out. If we were solving an equation, if a number factored out, the number could be disregarded, but if a variable factors out, the variable kind of needs to stay there, and either way, whenever we factor, we need to keep the GCF there. So the deal is, we factor out an x, so that would leave in its place x squared minus 2x minus 15. Now you might think that you're done there. You might think, well, that's it. Well, is it? Is that it? In other words, this doesn't factor any further? I think that does. So the deal is, we need to factor that a little bit further still. The x is still the x, and then we'll have x minus 5 and x plus 3. Okay? So, in case you don't know, all the stuff from chapter 4, finding the vertex, standard form of a quadratic function, vertex form of a quadratic function, intercept form of a quadratic function, foiling, all that stuff is requisite skills for chapter 5. I've been saying that all along, and I wasn't kidding when I said that. So if we look at this guiding, we got this x cubed minus x squared minus 12x. It's real similar to the last one. Factor out an x, that's x squared minus x minus 12. And again, we could factor that further still. X times x minus 4 times x plus 3. Okay? I would expect at this point in time that factoring, that you all would be really comfortable with factoring those kinds of expressions. Okay? So moving right along then, this key concepts box, there's that form, again with the standard form of a polynomial. It's kind of a mess. They're saying x minus b is a linear factor. So that's kind of important. X minus b is a linear factor. If x minus b is a linear factor, then b is a root of the polynomial function. B is also a root or solution of the polynomial equation. And B is an x-intercept of the graph of the polynomial function y equals p of x equals a sub n x to the n, blah, 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 blah. So all they're saying here is that the terms 0, root, x-intercept, solution, all those terms mean the same thing. They mean the same thing. They mean if you have some kind of polynomial function in factored form, like x minus 3, that's not a polynomial, that's a line. Well, it's a line, and it is a polynomial. If we graph that, that would just be a line that looks like this. Yeah, you're right. But remember, where the graph goes to the x-axis, that's the solution. If we had the equation x minus 3 equals 0, the solution would be 3. That's horrible writing there. X minus 3 equals 0, the solution would be 3. If we graphed y equals x minus 3, the graph's x-intercept would be 3. So the deal is the authors of the book, and me, want you to realize if x minus b is a factor, b is a 0, b is a root or solution, b is an x-intercept. Okay? They want you to realize that those terms are interchangeable, and also the fact that there's a counterintuitive component or counterintuitive nature to these roots, to these x-intercepts, to these zeros, to these solutions. Again, they're counterintuitive. It's x minus 3, and it ends up being positive 3 for the x-intercept, for the solution, for the root. Okay? So if we look at problem 2, I've got some graph paper in the notes. The book didn't do that, but I put a sheet of graph paper in these notes. I think it's a good idea to look at this. It says graph it. It asks, the question asks, what are the zeros of this? So to find that, we take y and replace y with 0. And we have x plus 2 times the quantity x minus 1 times the quantity x minus 3. The beautiful thing about this is already factored for us. We don't need to factor it. We just need to apply the zero product property. X plus 2 is equal to 0. So that tells us x is negative 2. That tells us that on the graph, our x-intercept is going to be negative 2. Also, using the zero product property, we can see that 0 is x minus 1, which tells us that x equals 1, which tells us our graph has an x-intercept of 1. Sound like a broken record, don't I? The final factor tells us that x minus 3 is 0, which tells us that x equals 3. Again, notice the counterintuitive nature of these, which tells us our x-intercept is 3. So you might say to yourself at this point, so how am I supposed to graph this? That's a good question. If we could have that thing in standard form, we would know our y-intercept. That's going to be a lot of work, a lot more work than I want to do. So the deal is, if I could find my last term, my constant term, if you would, that would tell you the c value. And that last term is going to be the result of all of the constants being multiplied. So if we were to multiply the 2, the negative 1, and this negative 3, if we found the product of all those numbers, in standard form, that polynomial would be y equals blah, 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 plus 6, right? So the interesting thing is then that plus 6 tells us our y-intercept of this graph is 1, 2, 3, 4, 5, is 6. Okay? We could have FOILed the thing out or distributed it, but ain't nobody got time for that. Using a similar idea, if we had the first term of this function, if we knew the first term, which would be the result of the product of the first terms in each linear binomial, if we knew the first term of this function, then we could determine the function's end behavior. I'll say that again. If we knew the first term of this function, then we'd know the function's end behavior. So I'm going to use my mint-colored toothpaste here. If we were to multiply x by x by x, we would get x cubed. And the fact that that first term of this function would be x cubed, well, let's see. The leading coefficient is positive because it's a positive 1. So that means on the end of this graph, the graph's going to be going upward. Okay, so the graph's going to be going up on the right. On the other end of the graph, since the degree is odd, that means that the end behavior is going to do the other thing on the other end. So on the other end, the graph is going to be going downward, right? So you might say to yourself, what about the rest of the points? I don't care. I really don't. I couldn't care less that you could do the rest of the points. You could plug in some values. You could plug in a negative 1. You could plug in a 2 and get some other points on the graph. But realize we have an x-intercept, an x-intercept, an x-intercept, a y-intercept. The end behavior tells us the graph's going to do something like that. Right? This graph's going to do something. I'm going to trace that before it disappears. Hopefully I can make it. There we go, there we go, there we go. I don't know how high or low the function goes, and I frankly couldn't care less. Okay? I do expect you all to be able to at least have the end behavior, the x and y intercepts. Okay? So hopefully that all makes sense. Just to confirm what we've seen here. Let's go to a graphing utility. I'll use Desmos. So we had x plus 2, the quantity. Desmos plays a little bit nicer with my smartboard. X minus 1 and x minus 3, I believe it was. Okay, so we did pretty good with our graph. We did real good with our graph. Notice the x-intercept of -2, 1, and 3. The y-intercept of 6. Okay, if we had plugged in some values, you know, like I said, we could have got a better idea. Again, also notice that the end behavior, the graph is going up on the far right and down on the far left. Okay. All right. So in this guiding, a lot of people forget what happens here. We have 0 equals x times x minus 3 times x plus 5. Some people, for whatever reason, seem to think that the x there is irrelevant. Well, I've got news for you. The zero product property says each thing, if a times b times c equals 0, then either a equals 0, or b equals 0, or c equals 0. So what I mean by that is we are going to have 3 x-intercepts. X equals 0. That's an x-intercept. Okay. X equals 0. That's one of our 3 x-intercepts. X minus 3 also equals 0. So x is going to equal 3. That's another. Boy, this writing, I'm not used to writing x on the right. But x equals 3. 1, 2, 3. There's another x-intercept. That last linear factor tells me that my other x-intercept would be -5. 1, 2, 3, 4, 5. Okay? So I've got my x-intercepts. Now the interesting thing is you might say, well, what about the y-intercepts? You might say, well, earlier you told us that we just need to multiply these constants. Well, yeah, I did. And you might say, well, -3 times 5 is -15. And you lied to us because this graph should have a y-intercept down here, but it has a y-intercept at 0. Well, what you don't realize is what we really had here was 0 equals the group of x minus 0, the quantity squared. And so 0 times -3 times 5 is 0. And so our y-intercept is actually 0. Okay. Our first product, the product of our first terms, our leading term, if you would. Let's get this box going. X times x times x is going to be x cubed, so we'll see the same end behavior as we saw before. End behavior would be up on the right, down on the left. Okay. And again, how far up or down does this thing go? Who knows? Who cares? It's going to do something like that. Okay, we could go back to Desmos, plug in those factors. -3 and +5. Could make a 0 here. All right. -3 +5. So there it is. Same end behavior. Down on the left, up on the right. Got our x-intercepts, got our y-intercept. There it is. Okay. If you really wanted to see how high or low the thing goes, you could zoom out. You could plug in values. Okay. I couldn't care less. All I care about, again, key ideas: x-intercept, 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 and the end behavior. Okay? So hopefully everybody's doing all right up to this point. There's this factor theorem, really big idea. When you take pre-calculus and you study polynomials, this is a huge idea. You're going to use it all the time. The expression x minus a is a factor of a polynomial if and only if the value a is the 0 of the related polynomial function. We've said it already. You know it. You just need to be able to apply it. Okay? So it's just saying x minus a is a factor. That's an a, not a 9. I better use a real marker. X minus a is a factor. So a is insert your favorite word, root. Solution to the equation, x-intercept. Okay. All right. Problem number 3. This is nice. I like this. In problem number 3, they're asking us to write a polynomial function. Now, the thing that's going to make this one tough is that they're saying this. If they didn't say that, it wouldn't be so bad. Wouldn't have been so bad. They're not telling us what to call it, so we could call it y equals. If you wanted to use p of x, that might be better for a polynomial function. They're telling us it's cubic, so they're telling us that these are the only 3 zeros. This negative 2 is a 0. This positive 2 is another 0. And this 3 is the other 0. Those are the 3 unique zeros of this. We should be able to work backwards because of that if and only if. Okay? There's a reason in math that we use these words, if and only if. Because of that, it means that statement's reversible. It means if a is a 0, then x minus a is a factor. So if negative 2 is a 0, then x minus minus 2 is a factor. Oh. So that would be x plus 2 is that factor. Yeah, that's what that means. It means that since 2 is a 0, then x minus 2 is a factor. Right. That's what that means. It also means that since 3 is a 0, that x minus 3 is a factor. Right. X minus 3 is a factor. So we could stop there, but you know, it does say standard form, doesn't it? Because of that, we've got our work cut out for us. A couple different ways of going about this. You could multiply these two first and then distribute the x minus 3 in. You could multiply these two first and then distribute the x plus 2 in. I'll be honest with you, there's one way in this particular problem that's way better, and I hope somebody recognizes it. I truly hope somebody recognizes which way is better. To multiply these two first or these two first? I'll give you a second to think about it. Is it better to multiply these two first or these two first? If you thought to yourself it's better to multiply these two first, you're right. Maybe another second to think about why it's better to do that. It's better to do that because that's a difference of 2 squares. When you FOIL that out, you're going to get x squared plus 2x minus 2x minus 4, which means the stuff in the middle is going to cancel out, which means that's going to just give you a binomial. Yeah. So that's going to be x squared minus 4, and that needs to still be multiplied by the x minus 3. Okay. So you got to be careful when you go to FOIL this. FOILing is still going to work. It'll still get you the right answer. So our final answer in the end then would be p of x equals. The first product would be x cubed. The outer product would be minus 3x squared. And we do want it in standard form. That's why I did notice I didn't put the minus 4x next. Okay, I will get a minus 4x, but I don't want to write it next. I want to write the minus 3x squared next because I do want this thing in standard form. And then finally, the product of the negative 4 and the negative 3 would be 12. Okay. So the nice thing about having a graphing utility handy is the fact that you can check yourself. So if we go to Desmos, we could graph this. We could graph x cubed minus 3x squared minus 4x. I think that's right? Yeah. And then plus 12. And then we could check, is the x-intercept negative 2? Yeah. And 2. Yeah. And 3. Yeah. We did good. We did good. Okay. All right. Number B here. It'll take a lot of work. I'm probably going to put B on a new page just because putting it in standard form, it's going to take some work. It's going to take up some space. Yeah. P of x is x plus 2. times x plus 2 times x minus 2 times x minus 3. Hopefully there's no question as to why that is what it is. A word of caution here with respect to, let's try that highlighter again. With respect to this, a word of caution, if you wanted to save yourself some time, energy, and space and say that that's x plus 2, the quantity squared, and say that that's x squared plus 4, you are so mistaken. You really should have been here yesterday and noticed that we said that there's no rule that says that happens. Yeah, that's bad. That's just really bad. Kind of like the last one, if we were to line these two items up and FOIL those out, that would give us a nice binomial again. It's a difference of two squares. So I'm just going to jumble this around. Now you could have multiplied that out and you would have got the same answer. If you don't believe me, try it on your own time. I'm not going to do that in this. But I'm going to jumble this around by the commutative property. So I'm going to put the x plus 2, x minus 2. Let me just use another color here for contrast's sake. The other x plus 2 I'm going to slide down there, and then the x minus 3. Okay? So hopefully you can see what I got going on there. So we'll get x squared minus 4. But you said, yeah, I did say the other one, but this is a special one. This is a difference of two squares. You got to know these. So the other result, this, when you FOIL that out, is going to result in an x squared minus x minus 6. Right? Now I hope we're that good at FOILing at this point. So now, I said it was coming. We got a binomial multiplied by a trinomial. Couple different ways to go about doing this. One of the coolest things that I've seen in recent years is this idea of horizontal multiplication. X squared minus x minus 6 times x squared minus 4. Setting it up like this. Kind of like you're going to multiply the old-fashioned way, where you take this negative 4 and you multiply that by the negative 6. And so you get 24, and then you multiply the negative 4 by the negative x, and you get 4x. And then you multiply the negative 4 by the x squared, and you get negative 4x squared. Okay. And then you multiply this x squared by this negative 6, and that gives you negative 6x squared. And then you multiply the x squared by the negative x, and that gives you negative x cubed. And then you multiply the x squared by the x squared, and you get x to the 4th. And then you combine all your terms. So the answer should be that p of x is x to the 4th minus x cubed. It's going to be minus 10x squared plus 4x plus 24. How could you check? A graphing utility? But what about the repeated 0? What about this? What's that mean? We're going to get to that in a minute. What that means is the graph should appear to be quadratic at that particular point. So let's go to a graphing utility and see how we did. Again, that means the fact that the 0 of negative 2 is repeated, the graph should appear quadratic at that point. When x is negative 2, the graph better look like a parabola. So we got x to the 4th, minus x cubed, I think it was, right? Minus x cubed minus 10x squared. Minus 10x squared plus 4x plus 24. Plus 4x plus 24. So remember, the graph should look quadratic when x is negative 2. X-intercepts should be 2 and 3. So let's zoom in a little bit. X-intercept 2, x-intercept 3, x-intercept negative 2. The graph looks quadratic when x is negative 2. Bam, we got him. And behavior is up and up. Leading term is x to the 4th. It all makes sense. Y-intercept should be 24. The y-intercept should be 24, and the y-intercept is 24. We're good. All right, maybe you didn't like that way I multiplied that. Maybe Maybe you like the distributive property. That's fine. That's fine. That's no problem. If you like the distributive property, let me put that kind of big enough to, maybe I have to undo that. I don't know. If you like the distributive property, we could have gone crazy here. We would have had x to the fourth minus x cubed minus 6x squared. Distributing the negative 4, we would have negative 4x squared plus 4x plus 24. So then our p of x would have been x to the fourth minus x cubed minus 10x squared plus 4x plus 24. You get the same thing, so there's more than one way to multiply those out for sure. Okay. Just thought that horizontal multiplication was kind of neat to see. Okay, that horizontal multiplication is kind of cool. All right. So graph both functions. How do the graphs differ? How are they similar? So this other p of x was x cubed, no, x to the fourth minus x cubed minus 10x squared plus 4x plus 24. Okay, so they say graph both of these. So let's look at both of them graphed. The first one in example A, x-intercepts at x equals negative 2, positive 2, and 3. Y-intercept of 12, which is kind of up here, and behavior of the graph is up and on the right and down on the left. So that graph's going to kind of do one of these. I kind of messed up in the middle there. That's supposed to be more like that. Sorry about that. See if I can get real precise here with my eraser. Not bad. Okay, good enough for now. And then the other function has similar x-intercepts. An x-intercept of 2, an x-intercept of 3. But the x-intercept when x is negative 2, the graph ends up being parabolic there. Okay. And the y-intercept was really high on this one. It was 24, so this one's going to go up twice the height. So this one's going to do something like this, and something like this, and something like this, and then something like that. So the graphs kind of have some similarities. Let me go back to full screen here. So again, the real big idea to take home from this is right there. If we have some kind of factor of x plus 2, the quantity squared, just look at that. That would be a parabola translated 2 units to the left. There it is. Okay. So I think we're good there. Dotting, I think you can handle one of those. No need to run through all that again. Again, the plus 3, the minus 3, that would make that work out pretty nice with a difference of 2 squares. So here they're talking about multiplicity whenever a 0 repeats, kind of what we just looked at. If a is a 0 of multiplicity n in the polynomial function, blah, 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 the behavior of the graph at that point will be close to linear if n is 1, close to quadratic if n is 2, close to cubic if n is 3, and so on. What they're saying is just what we said a second ago. If you have a factor that's raised to the second power, the graph's going to look quadratic there. And if you have a graph where a 0 is cubic, the graph is going to appear to be cubic there. So we probably ought to have a general idea of what cubic functions look like. So for that, let me go back to Desmos. A basic cubic function kind of does an S. Kind of does an S around the origin, okay? A basic quartic function looks quadratic. A basic fifth degree function looks like a cubic. Okay? Very rarely will we see any multiplicities that high. But it could happen. So the big thing to realize is that a cubic function in the general case looks something like that. Okay. So let's see if we can figure one of these out. What are the zeros of and what are their multiplicities? Ooh. So we're going to have to do a little bit of factoring. Chapter 4 stuff. F of x is x to the fourth minus 2x to the squared to the cubed minus 8x to the squared. So notice that the GCF here is x squared. So this would be x squared times the quantity x squared minus 2x minus 8. We should be able to factor that further still. This would be x squared. If you'd rather, x minus 0, the quantity squared. Maybe that's going to make that more clear for you. Times the quantity x minus 4 times the quantity x plus 2. Okay, so that's what f of x equals. The question asks, what are the zeros? So here we go. The zeros are 0, 4, and negative 2. The question goes on to say, what are their multiplicities? Their multiplicities, it's kind of weird. If the zero only happens once, we really don't need to mention it, but they say, what are the multiplicities? Well, for the 4 and the negative 2, their multiplicities are just once. It's a singular zero there. It only happens one time. The graph's going to look linear at that point. What about the 0? That multiplicity is a multiplicity of 2. So I need a sheet of graph paper because we probably ought to look at what this graph is going to do. Okay, based on everything we've been studying, the graph should look quadratic when x equals 0. The graph should look like that. The interesting thing is it might look like that. We don't know unless we consider the whole thing. Okay, but it should nonetheless do that. Or maybe that. Okay, so we'll put that off to the side. The graph should look linear when x is 4. When x is 4, when x is 1, 2, 3, 4, when x is 4, the graph should look linear. What that means is the graph is going to do something like this, or maybe something like that, but the graph should look linear when x is 4. Similarly, if this will let me clone this, maybe it won't. Clone. There we go. Similarly, when x is negative 2, the graph should look linear. Okay, we don't know what kind of linear it's going to look like, but we do know it's going to be linear there. Okay. So the end behavior is up and up. So on the ends, the graph's going to be going up and up. Our y-intercept is the same as our x-intercept. It's 0. Another x-intercept when x is negative 2. Another x-intercept when x is 4. So the graph's probably going to do something like that. So in this particular case, the only way that the graph's going to be going up that way is if we have some kind of parabola doing something like that there. Okay? We don't know how far down it goes in the middle. We don't care. We couldn't care less. Kind of looks like a W, or maybe a shark or a fish, or I don't know. If you consider this general shape. See if I can group all that together. Doesn't that kind of look like a shark? Done it. Done it. Done it, done it, done it, done it, done it. It's a shark. I don't know how well this is going to come out in the video. Have this thing fly in from the left. Done it. Maybe I shouldn't do that. All right. Enough horsing around. Okay, you can stop now. There we go. Oh, and now I got my crazy graph paper going on too. All right. X to the fourth minus 2x cubed minus 8x squared. So let's try that. See how we did. X to the fourth minus 2x cubed. 2x cubed. Minus 8x squared. We did good. Quadratic there. Linear there, linear there. Who knows how far down it goes? Who cares how far down it goes? Okay. If you wanted to know how far down it goes, again, you could plug in some numbers. Relative mins and maxes, you're going to need a graphing utility for those. It's just kind of saying on a particular interval on this slice of the graph, there's a minimum there, there's a maximum there. You're going to need some kind of graphing utility to find those. So I think that's it. Yeah, there's a story problem with the box. We'll talk more about that tomorrow. So it's been real, it's been fun. I hope everybody found this educational. Sorry there weren't any super good bits of comedy in there, except maybe the shark, I don't know. Anyway, I'd like to give a shout out to the future Mr. Minnick for being such a cool guy. Probably sitting in the back of the room taking notes like a good student would. So it's been real, it's been fun. Have a great day. See you all later. Goodbye.